Hi. So welcome everyone. This talk is Rage Against the ADRs, using machine learning models to detect and stop authorization bypass vulnerabilities. Yes. And this is me. I'm Juan Berner. There's my Twitter and my blog post. I'm a security lead developer at Booking.com and also working as a team lead managing one of the application security teams. I usually work with application or infrastructure projects, and in particular, this is a research done on the application space. So this is a bit of the overview of the talk. I will be talking a bit about what IDRs and other authorization bypass vulnerabilities, then how we can prevent them, and also why prevention is not enough. Also, afterwards, about how can we detect these attacks and block against them. And finally, if we have enough time, a demo. So yes, IDR. So it stands for Insecure Direct Object Reference. It's a very commonplace vulnerability, and it's incredibly risky, in particular because of the lack of technical skill needed to exploit it. There are some cases where you might want to do things like a blind IDR, which is more technically difficult. But in many cases, we're talking about something like in this image, where you might have somebody requesting a resource for user 1000, and then they can go to access other users' resources like 1001, 1002. And this is also very much a live vulnerability, so this is actively exploited in the wild. There's a lot of bounties for these vulnerabilities. This is not going to be so much about how to find them as an attacker, but how to actually defend against them from the defense perspective. Now, just to cover, there are other types of bypass vulnerabilities that this type of detection I'm going to talk about and protection also covers. So while IDR can be considered some kind of horizontal authorization bypass, because you're accessing somebody else's resources, it could be also the case that you might have an authorization bypass to access a higher level authorization resource like an administrator account, or cases that you are just avoiding controls. So for example, if you're able to act on endpoints which are not supposed to happen before some kind of check, like being able to add a phone number for an SMS before you actually pass to FA, allowing you to just add a phone number and then pass to FA, making 2FA redundant. Now, when I started looking into this, I started trying to map all the different ways that these kind of vulnerabilities could be added. So in some cases, you might have an endpoint which has an authorization check, but then the endpoint might fail or somebody might skip that check. So going there, the red parts are like attacks, and the blue parts are detections, and the darker blue are conditions. The point here is that there are a lot of different ways you can add these vulnerabilities, but there are overlaps on how you can detect them and prevent against them. So going into detail on some of them, because there are plenty, but for example, it might be a situation where a condition is ignoring a check. So in this particular code, we had some check of, is the user logged in? This is in Go. And then there's another check of, okay, can this user access the resources of the user who they're requesting? Now, there might be a condition that allows you to ignore the authorization check. And in that case, you are actually executing the same check, but you might ignore the result. This might happen if somebody changes the Boolean logic for that authorization check. And there you have like the decision tree of how this can happen, because there is some check in the endpoint and it happens, but it does not succeed, but yet you're still giving back the resource. A different situation is when you might skip the check altogether. So for example, there might be a condition that allows you to skip. Funny enough, we just had a talk previously where one of the vulnerabilities was exactly this. There was a situation where there was a check for the path, and if the path matches a particular string, then you might actually ignore a check to see if somebody can access a resource or not. And here comes a bit of the part of the rage to IDRs, because it's very hard to detect them, and this is one of the particular cases for this, when there might not be a check at all. So somebody creates an endpoint that gives you back credit card information, or in this case, information that's only for friends, and they just forget to add a particular check for this. And in this situation, even doing code review, you will not realize if this is actually something that should have a check or not. So up to here, that's what we are dealing with, authorization bypass vulnerabilities, and in particular IDORs, where you reference a particular object, and that's where the direct object reference part comes in. But can we prevent against them? We can do some stuff to prevent it, at least at that layer, like, for example, enforcing random identifiers, so you cannot just guess the user ID. In the previous example, it would be very hard if it was like a 30-character string, each different user. Then you can do access control through the models, use static application security testing, but usually the issue is it enough? And that's where detection usually comes in as another layer of defense in depth. But the current ways that we have to detect these kind of attacks are very limited from the detection space. So you might have the enumeration where you realize somebody is going through different users, and you might add rate limiting, which is basically I will detect after a threshold and then block that attack. Then you might have hard-coded rules for this, but usually the big difference here is that you're looking at attempts and not actual success of exploitation, which can lead to teams getting a lot of alerts. They don't know what's going on, they don't know how to act upon them, and they can't really realize somebody has stolen data or not. And that usually leads to alert fatigue from teams. Now, how I got into this was basically around this kind of stopping the process of whack-a-mole, because after working on implementing a WAF, the big issue was this kind of attacks, and there was a team which was implementing these kind of authorization checks out of band. So every time they would find some kind of authorization check, they would recreate that out of band, and that was a very slow process, involved a lot of code reviews, case-by-case basis, and it was evident it would not scale because we had humans looking at code and trying to understand what was the authorization check needed and implementing it afterwards. So the idea was, okay, how can we actually detect this in a scalable way? So I started looking at this problem at its core. So it's a classification problem. So we need to classify if authorization checks are needed or not, or what's the result around them. The application currently uses the context to be able to classify it. And these authorization flows constantly change. So even if you do it hard-coded one by one, you will never adapt to how quickly an application can change. So here, it's the question of how can we improve from this current situation. So for one, we can really understand the request flow, what's going on each request. We can try to go from the possibility of exploitation that most current detection tools do to actual exploitation attempts. So we actually know and we alert someone when we have a vulnerability being exploited. And in this way, we could try to either imitate or predict what the authorization is doing, but in a generic way. So you don't need to hard-code it or change it every time the application changes. So what do you need to do this? First of all, you will need to really understand the context of your request. So when your web application comes and somebody is trying to access a resource, you need to have information about what the request is doing and what's the context around that particular request. Then you would want to ensure that the authorization logic is centralized in a way that you can depend on this kind of metadata being added. And you might want to predict the result based on the context. So to make it a bit more visual, when we're dealing here with machine learning models, you would want to have some kind of a series of requests which will happen. You will get the data from those requests, and then you will provide this model and you will train it based on the context of the request and the authorization result. So for a particular context of a request, did the request fail or the authorization result fail or succeed? And afterwards, on the prediction side, you would want to be able to, again, push to this model, hey, this new request has happened, there's this particular context, this was the authorization result. The model, without looking at the authorization result, is going to predict, I think that this should have been a failed or successful authorization result, and then compare. If the comparison does not match, then you can say something is going wrong. And the key part here is that you don't care, at least in my case, you might not care if an authorization check is harder than it should. But you really care if you predicted that there should have been an authorization check and you are not seeing that authorization check happen. So first, let's start with the context part. So at the left, I have a typical Nginx access log, and at the right, what I have as a log of my request. So usually, I add a lot of context on the request. So you have authorization results at the top, some database activity, which might be API calls, if this was talking with a service, and information on the response. Then we have the authorization information. Here you might have a library, a sidecar, or an agent. And you're basically ensuring that authorization checks happen, but they also add data to the request. A key point here is some of the challenges of this. First of all, centralizing authorization checks. This means that not everybody is implementing their own authorization libraries, but also ensures that you are getting the context that you need to be able to predict these attacks. And also, the applications might not behave as expected. So, for example, you might have APIs, and you might say, okay, I can trust their status code as a success or failure, but it really depends on each API. Now, on collecting the signals from the request, as I showed before, there's performance information, interaction with services like caches, databases, or APIs, or authentication information that you might use. And here I have some examples of this request. So at the left, you have a successful authorization. At the right, you have a failed authorization. And there's a lot of data there, which I will go a bit deeper, but you can start using this data to, without looking at the top part, just by yourself, you could start predicting, okay, this is what I would have expected the authorization result to be. So this is a bit more clear. So in this case, you can see that for a failed authorization, which is a 0, the number of database calls is lower than for a successful, which makes sense, because if it succeeds, then we are actually getting the data back. If it doesn't succeed, we are returning the data. Now, how can we use this data? So one of the supervised learning models that you can use is decision trees. This allows you to create this kind of rules based on the data so that your system can learn from the amount of data you have. Some issues here is that you want to avoid overfitting, and there are solutions to this, such as random forest or gradient boosting machines, which are models which are built from decision trees in different ways, random forest in parallel, gradient boosting one by another sequentially. But in the end, they allow you to reduce the overfitting and give you a better model that adapts to new environments. So let's say that we have this data and we want to be able to predict if there's a successful or failed authentication. So we would be using, for example, random forests, which will create small trees, which are going to be used in ensemble. So for example, one tree might say that if you have less than 3 operations, then if that's the case, it might mean that you actually failed your authorization check, or it succeeded. And it might use a lot of them to make a decision afterwards. Now, there's a limitation here. What happens if you always request data before actually making an authorization check? In that case, for example, I call it preload. You might get the data first, which is strange, but not unheard of. I have seen it plenty of times. And then you actually do the check and decide to send back the information or not. In this case, what will happen is that the model is not going to be much better than a coin flip. You're going to be in a situation where you're basically just guessing, because it's the same amount of data requested. And unless you have other features that you can use for this, you're not going to be very good at predicting if this was a failed or successful authorization check. So that's where the approach I just showed doesn't pan out anymore. But we can actually overcome this by adding more features to our data. So up to now, we were using features which are just signals of the backend information, API calls, database checks, information, even the wall clock, although it's not a great feature for this case, but information of the request. But what if we could use information from the response itself? So in that case, we might go, okay, I will use the content size. So if it's a larger content, it means I'm returning data. If it's a small content, I'm not. If you do that, then you have an issue of APIs that might return you the same amount of content, just with a failed message. And when it's a successful message, it might return you the good information. But like in this case, there might be some patterns that you could see and that machine learning models could also learn. So for example, when it fails, it's always sending an incorrect user not allowed message. But when it's successful, it's sending some other information, like creator name or biography. Now, there's an issue with this. We might say, okay, let's just pump all the data and learn from this. But you might not want to do this directly, because this might be information of your users, you might want to protect it, in some cases it might be even credit card information that you're returning. In other cases, it might be compressed, so that's something you would deal with this depending on where you're consuming this data. And it also can change a lot. So for example, if you have translation services for every single language, your content will return. Like the key names is not going to be biography, it's going to be biography in a different language. A good part with that is that as long as you have enough data and a good distribution of your users, you will still be able to learn from these differences. But on the content itself, you might not want to use the content by itself. So for that, start looking at how we could anonymize this content. I came up into two most probably, there are all solutions, but the best ones I saw, one was around context-triggered piecewise hashing, which I will explain what it is. And the other one is something I just call partial hashing, but you could just consider it hashing. So first, on context-triggered piecewise hashing, this is a very cool hashing algorithm or fuzzy hashing algorithm, which allows you to, instead of just creating a normal hash, which if you change a single bit, it might change the whole hash. If you change part of whatever you're hashing, it will only change whatever local part you are changing. So this was introduced, I don't remember exactly when, but to deal with malware and to be able to find a malware that might change parts of itself and still be able to identify it through a hash. In this case, for example, you can see that the first string, what changes is just adding smarts. But since this is looking at context and finding a delimiter, which is the word cat, it can only change one part of the hash and not the whole hash. And it's going to be useful for us. So for example, if we have a whole HTML website, we can create this kind of hashes, which are going to change only on the different parts which the website or the HTML changes. If you remove the content itself, you might only get the structure of the HTML tags. And as long as this is not randomized, you can get a pretty good picture of what's going on without accessing the content itself. So when I was looking into this, I started trying to find, okay, how can I do these differences, going through text differences, but then I realized this could also be done as an image classification problem. If you get every single one of the characters on the hash, transform into some kind of color, then you can start seeing some patterns. In this case, it was a failure and success. One of the changes is, of course, the response size, but other are the different colors which are displayed. And similar results have similar colors. Now, I tried to find a way to really have a very good prediction around this. So I started with normal machine learning models like linear regression and SPMs, then tried some unsupervised models like clustering. And what really showed promise was using something called convolutional neural networks, which is used a lot for image classification. But in the end, it didn't have the accuracy I wanted. I was aiming for no false positives, or pretty much no false positives. And this still was quite hard because taking it as an image classification, it's not exactly perfect. But in some cases where other models might not work, it might be the best approach there. So the second approach I went for was around the pre-hash or the partial hash. So if we get the same data, either HTML or JSON, and we start trying to create one-way hashes of the data, and in this case, since I don't care so much about collisions, I could even get partial parts of that hash. Of course, the hash would be salted and the salted would be secret, but this would allow you to start getting some information of the data, even if you don't know like the name biography or somebody's called Ashley, you might still be able to use that information for learning, because what you would be looking would be patterns. Are there particular words that appear more? And even if you don't know the word, just getting a hash which might have collisions is good enough. So in this case, instead of random forest, I started using gradient boosting machines. So gradient boosting machines will allow you to create these different small trees, which might learn, for example, a particular hash. If it's missing, it means that there's a correct authorization, and a different hash, if it's there, it means it was a failed authorization. So without having the actual data or knowing that a word says incorrect login, it learns from it based on the amount of data that has been fed to the machine learning model. Now, up to here, we have covered two different situations. One situation was around, okay, how can we use backend signals? And the other situation is how we can use the information of the response. But in both cases, we had something which was key, which was the actual authorization information. So we were able to say, based on the context, I can predict if this was a successful or failed authorization attempt, so that if for some reason I see that I'm returning content that looks like you passed an authorization check, but you did not pass the authorization check, or that authorization check is missing, then I have learned, okay, either there was an anomaly, because I was expecting this particular check of you can access a resource and it's not there, like in the second example I showed, or I will see a difference. I see that there was a failure on your access, but I returned you the information, or I saw enough queries to do this. So that's all information we learned from the context. But what happens when we don't have that information, as in the third case? So that's the most tricky one, because in this case, we're actually trying to go and find out, should somebody have added an authorization check here? And there is no information for us to learn, but we do have other information. So just to mention a small detail, before I was looking at different models, and each was trained on each particular endpoint, learning by, let's say, /login. In this case, I'm going to be looking at all the information from all the endpoints, so every single endpoint, and learning. So what are we going to learn? So in this case, we had the message for friends endpoint, and there was no authorization check. But we did have a request for information. In this case, for example, on the table user, the call message for friends, we returned the information. Even better, I didn't do it for this example or demo, but you could actually check, is this a column that doesn't refer to the particular users? And the same way it could be with API calls, what API calls information you're accessing. So here again, I went with random forest. But the interesting part here is that this can become very deep decision trees, because what you're trying to learn now is, based on the information that the request got, would I have expected there to be an authorization check? So if I'm I'm user A, I'm requesting information from user B, based on the behavior of all the other endpoints, and the particular resource I'm requesting, like for example, this message for friend columns, or it could be some column which has private information. Is this an endpoint that usually has an authorization check, or is it an endpoint that doesn't have an authorization check? So for example, you would expect that public columns, if you had a decision tree, they would find, okay, it's this particular column never has an authorization check. But there might be another column or a combination of columns which do have this kind of checks. And that's what you want to learn from this. Now, up to here, we had to build these models. Now, you can either do it as a very large model, or you can have separate models. In my particular case, for the first two situations, I decided to go with particular models for each particular endpoint, and also for each particular authorization path. By authorization path, I mean, in this example, how does the flow go of a request until you are actually returning something to a user? So, for example, it could be that the user gets logged in, and that's a failure, request finished there. Or it's a success, and in that case, it might fail, or it might succeed on the user current user check. So each of these cases are actually splitting your data into smaller subsections, and they explain you about a particular flow, what is the behavior of that particular flow. So in this particular behavior, in this particular flow, when users fail, are they requesting data from a database? Are they not requesting data from a database? And this helps on the second condition I showed of the skip check. Because if we go back to the example, you would expect that even if we talk of the example of the image path, you would expect that if you are going to access a CGI resource, and there was a failure, there was a skip on the authorization check, so it was not done at all, you would see for this particular path, which might have been, let's say, is user existing, not checking anything else from authorization, fail, you might say, oh, we're actually executing a CGI. So that would be an anomaly that your model can learn. So there's the benefit of doing per authorization path, that you can cater for these anomalies that might not have been learned. And that would mean one of two things. Either this is a new behavior, which might happen when you're rolling a new application, not when you have the same code for 1 year or even 1 week, or this might be someone exploiting a vulnerability. So now on the training part. One key part here is that you want to make it as representative as possible. So depending on the size of your website or application, you might get a lot more data, or you might be very constrained on the data. But if, for example, you have multiple users of multiple countries, and there is one country which is more active at one particular hour, well, a single hour of the day might not be enough. There is no rule on how much time you will have to depend on your data, but the key part is that you just focus on making it representative. And one thing you can do is just start watching for errors, and once those errors start disappearing, you might say, okay, my model has learned enough at this point. Then you might want to start going from the alerting to blocking to detecting anomalies. So you don't want to start from blocking at the start. And in some cases, as the one I showed for detecting columns which should have an authorization path, you might want to start with alerting only. Then you might want to adapt to new versions of the logic as they are introduced. So for example, every time that somebody is rolling out a new application, let's say they're deploying some new container image, you might want to pick up on these changes and start training a new model based on this new version of the application. So if somebody changes an authorization path, you're not going to be blocking normal users. You're actually adapting to, okay, this is the new normal. Of course, there's the danger here that somebody might be exploiting the new vulnerability exactly in the first seconds that it's released, which should appear as an anomaly. It shouldn't be a constant behavior, and you should be able to detect against it. Or worst case, at least the risk has been reduced to this particular moment in time for code which was not present in the past. And finally, around online training, that's also a nice possibility. It cannot be done with all the models. It solves some of the problems. For example, if you're training neural networks on the actual content of the response on the same web server, let's say in a parallel way, you might not have to worry about encrypting the data or hashing the data because it's going to be compressed as part of the new bindings of the neural network. Now, up to this part, we were covering on how to train the models. Let's say we now have those models available. First of all, you can detect this by out of band. So you're collecting all this context information I showed before, and then you are executing these checks by replaying this information to the models and checking what the models predicted against what the request said. The key part here is that you want to avoid alert fatigue. This is the nice thing about this. From this perspective, the logic and what happens in this kind of decision trees is very fixed. So applications don't usually change the amount of database calls they do without doing a rollout. So that means that the threshold for errors is very small. And then on blocking, it really depends on how you want to do it. I have spoken in the past on how you can do hybrid blocking architectures, but in this case, and for the demo, I just did it with an inline model, which means that every single request, I'm actually, before sending it back to a user, I'm giving it to the model to check the information, the context, does it look exactly to what you were predicting? If not, do not return the information. And one more comment, because I didn't have a lot of time to cover this part, but the same things I'm talking about from the read perspective, like reading databases, you could implement it on the write perspective. So, for example, there was a paper from Facebook on invariant detection that they did using their graph database. And one thing they do is they try to, in a very different way, but they try to replicate authorization checks. So not predict them, they actually run them again before their graph database, if I remember correctly. In a way, we're not going to do that, but what you can do is you can hook into the write calls. So even if it's a service call to an HTTP service or a write to the database, and execute the same logic. Up to this point, collect all the context of the request and compare that context to your prediction before a write and decide, is this what I expected or not? So for example, if you're writing to a particular table, you could check, okay, I expected to have this authorization check to succeed or to have it at all. So now I will try to do a demo. Basically for the demo, what I did was I repurposed a form I had, added IDORs to it, then created 10,000 random users and started having them interactions with each other. So I could actually build the models and then I could add them for the blocking part. So let's see. For that, I will go to a website. Oh, of course. Yeah, I have it here. So I built a domain for this. So these are normal websites, a very small forum where you can go and you can get some post and then you can access the data. So in this case, I will just grab a random user like this one. And I can log in as the user. Of course, it's a very simple password, but it's fine. And now what I'm going to do is I will also grab another user. So first, as the normal user, I will go to my profile and check my information. Okay, everything's there. But what if I try to do an IDR? So we'll try to access based on the username. So now it doesn't work. Fine, there was an authorization check. But if we add the ignore auth parameter, okay, now it works. Now we got a message below, basically because I have the detection mode on for this. So basically there was a model which was running, and that model checked, hey, is this the prediction I had? And if not, the prediction would be, oh, wait, I will try to put this up here. So, well, let's go through it. I will just connect to my container. And I will check the logs so you can see the information that just happened. So as I showed before in the logs, here we had just one request to the other user, and the authorization failed. Yet we were able to get all this information. And that's why the model actually learned from it. It realized, okay, this was not what I expected. So for example, if I now change the mode to block. Okay, we'll do it. This was not expected, but I can just change it from a database. So now if we go to our website, everything works. Yes, it doesn't work anymore. So you're not getting the data anymore. Basically what's going on here is that based on this information, now the model executed, checked this, and realized, okay, this was not what I expected. So if we compare before, this was the previous one, when we were not adding the ignore auth check. So just by looking at the request, it also failed, but it's obvious that we did not execute the data, the request that we wanted. So from here, you can realize that this context, and in a way, if you think about the keynote, how we're talking about the different organizations and they use the metadata, we're using the metadata of our request to learn from them and to predict what should happen. What do we want it to happen? And the key part with this authorization bypass vulnerabilities, so it could be with an IDOR, or it could be with something like a vertical privilege bypass, they always have some connection to a context. So if you are able to access as a normal user a resource of an admin, and you are logging information of is this user an admin or not, you will realize we have a user with a particular security clearance, which is accessing a resource where every single user that accessed always had a higher security clearance. So in a way, you can treat this as an anomaly detection or a basic way of just blocking whatever is not expected. So you are enforcing learned behavior from the application. So some general notes. As I mentioned before, you can use a single model, but you should take into account your environment, if it makes more sense or not. Then these technical flaws, that can lead to authorization bypass vulnerabilities is going to allow you to be able to detect these anomalies, but also learn a lot about your context and your application, because this really helps you map how your application works, the different ways it might behave, and in a way, this is information that most people, even developers, do not fully understand of the product, especially if it's a product that has been hacked on by different people over and over again. And I mentioned on the API status code, and as a general note, what I would take from this is that we have a lot of information on our request. It's not normal for people to actually use it, but it's very valuable. And if there's something that machine learning models excel at, is by getting a lot of information and learning from it. And if you think about all of our security, at least in application security, what we're trying to achieve is that applications continue to behave as we expect them to behave. And in most cases, this is going to be in the correct way of behaving, or the normal way of behaving. So that's information that you can leverage to be able to detect this, not just authorization bypass, but other types of vulnerabilities. So yeah, you can find me on Twitter, and if I have any questions, this is a good moment, or just send me or find me somewhere. So yeah, thank you very much.